Hello everyone, my name is Nick Fraser. I am a software engineer at Structura Biotechnology. Today I'm going to talk to you about CryoSPARC Tools. This is a software package that we've developed to facilitate advanced cryo-EM processing in CryoSPARC via Python scripting. I will show you how you can use CryoSPARC Tools in your own advanced workflows. Here's what we'll cover today. First, we'll take a look at an example problem that you might encounter while doing cryo-EM processing that doesn't have an obvious solution in CryoSPARC. I'll introduce you to CryoSPARC Tools and how it works. I'll show you how to solve that initial problem with tools. I'll give you a quick overview of some use cases that CryoSPARC Tools works really well for, and then I'll point you to some learning resources to help you get started. Let's take a look at our sample problem. So here I have a simple workspace in my CryoSPARC instance. I have some exposures that I processed earlier in live. I imported some particles that my colleague Hannah has kindly picked out from this dataset. I extracted the particles, used the alignments from these picks to reconstruct a volume, and then I ran a final refinement where I get a pretty good resolution of 2.9 angstroms. Now, as I scroll through my diagnostic plots here, I'm noticing this per particle scale factors plot looks a little interesting. So what is per particle scale and what exactly does this plot mean? Here I have an illustration of a cryo-EM sample from the side. So if you can imagine, the electron beam goes down through the sample, it hits the sensor below, and an image is captured. You'll notice in the sample, the ice towards the left is significantly thicker than the ice on the right. This means more of the signal from the electron beam will be blocked by the thicker ice, and so particles at that location will look a little noisier, and will not include as much detail as particles captured in thinner ice. In CryoSPARC, we call this per particle grayscale, or alpha. We compute this value for each extracted particle during refinement jobs based on how much signal each one contributes to the final volume. So now we can interpret our plot here. It looks like in the sample, most particles have alpha around 1 or greater. This is good. This is generally what we want to see. Although we do have this peak of particles that have alpha around 0.9 or lower. I'd like to know, can I improve the quality of my final volume if I filter out the low alpha particles? New versions of CryoSPARC have a job that can do this, but let's say that job didn't exist, or there was another quality that we wanted to filter our particles by that CryoSPARC doesn't yet support. How would we do this? This is where CryoSPARC Tools comes in. CryoSPARC Tools is a Python module that facilitates writing custom cryo-EM data processing scripts with CryoSPARC. So let's break this down. A script is a text document with processing instructions, kind of like a recipe where the steps describe anything that you'd like a computer to do. Python refers to two things. It's both the language that scripts are written in and the name of the program used to execute them. A module is the name for a Python script that provides some common functions and instructions. That way, whenever you write a new Python script, you don't have to manually copy those common functions into your script every time. It's modular. So that's CryoSPARC Tools at a high level. Now, how does this actually work? The blue rectangle here represents a local CryoSPARC instance. It's a very simple instance. It just has one job inside it. Let's say we'd like to do something with these particles. For example, filter out the bad ones, train a machine learning model, write them out to rely on, anything you want. We can write a Python script that includes written steps to download the particles data, inspect and process that data, and save the results. This script can run anywhere, even on your local macOS or Windows machine, as long as you can access CryoSPARC from a web browser. You can execute that script with the Python command, which runs the steps defined in your script. The last step in your script will write the results back to CryoSPARC as a special job type called an external job. And once you have that, you can use it like any regular job. You can connect its outputs to another job and continue processing. The key idea here is that anytime you want to do any cryo-EM processing that CryoSPARC doesn't yet support, you can use tools to do it. CryoSPARC Tools is designed to work on data within CryoSPARC projects. So the key to learning how to use tools is to first understand how projects are internally organized. If you've used CryoSPARC before, you'll be very familiar with this. So here I have a representation of a single project in CryoSPARC. In here, you'll find one or more workspaces. Each workspace has one or more jobs in it. A job may be linked within multiple workspaces. And jobs are defined with various metadata fields. For example, parameters, a title, its scheduling status, and most importantly, jobs contain inputs and outputs. Each one of these represents some kind of cryo-EM data type. Most typically, you will see exposures, particles, and volumes, and there are some other types that we support in CryoSPARC, such as templates and trained models. So in this example, the blob picker accepts micrographs as input and produces particle picks as output. Depending on the job type, outputs have context-specific results that they produce. Here, the blob picker's output contains the particle locations and maybe some computed statistics, but it doesn't contain other relevant results that we might need in some connected jobs, such as extracted particle images on disk. To get those results, we have to connect the particles to the input of a job that produces them, such as an extraction job. Each input has slots that expect specific types of results. This is what happens internally when you drag an output into an input in CryoSPARC's job builder. It matches up the results in the output with the corresponding slots in the input. If you connect an output that doesn't have a result that the input expects, say for example, that this blob picker job was missing the location result, then the extraction job will not run until it has that result. When you have everything connected, you can run the extraction job, and this produces a new output with the same particles that you provided as input, but with the new blob and CTF results added on. You can keep going with this. An ab initio job will expect a particles input with blobs and produce a volume output. One final data type that you might encounter is events or event logs. These contain text logs or images that occurred as the job ran. You can see these from the Events tab in the CryoSPARC interface when you open up a job. CryoSPARC Tools is designed to work in this entity hierarchy. Everything you see here has a function in CryoSPARC Tools that lets you access it by calling functions that traverse this hierarchy. How this works in practice will be very clear once we do our demonstration. So before working with CryoSPARC Tools, you need some basic Python programming knowledge. If you haven't done scientific programming with Python before, we've linked some resources in the description that you can take a look at. You'll also need CryoSPARC version 5 or newer, and you'll also need a Windows, macOS, or Linux machine for running scripts. Now, CryoSPARC itself can only run on Linux, but CryoSPARC tool scripts can run on any modern operating system that has access to your CryoSPARC instance, including the same machine. Now we can jump back into our CryoSPARC workspace. We have the refinement job here with 300,000 particles that we'd like to filter by their per particle scale. And here on the right side, we have Visual Studio Code. This is a text editor I installed earlier with a built-in terminal that I'll use to run commands, but you can use the terminal that comes installed on your computer and any code editor that you like. So in order for me to run the script, I first have to install CryoSPARC Tools. I'm going to switch over to the tools documentation, which you can find at tools.cryosparc.com, and I'm just going to install tools according to the instructions here. So in the terminal, we'll first run a version command to verify that Python is installed. Okay, great, and my Python version does match the minimum requirements. So from here, I could run pip install directly, but first, I'll create and activate a Python virtual environment, just so that I don't interfere with my global Python installation. Now I'll run pip install CryoSPARC Tools. There's one last thing we need to do before writing our scripts. I have to log in from the terminal. So just like you would log into CryoSPARC from your browser, you have to do a similar login step when setting up tools, otherwise our scripts won't be able to connect to our instance. So I'll run this login command here in the documentation. And for the URL, we'll use the same address that I used to access CryoSPARC from my web browser. So that's this localhost URL here. Here, it'll prompt me to enter my email and password. Okay, now I'm logged in. Note that you only have to do these install and login steps once, though you may have to log in again later if it's been a while since you last ran a CryoSPARC tool script. And with that, we're ready to write our script. So I'll close my terminal here to reveal that, I've already written the per particle scale script. You can see it's pretty short, it's only about 30 lines. Now we could run this script directly in the terminal by writing a Python command with a file name as an argument. But instead, we're going to run this script step by step in a Jupyter notebook so that we can better understand what the script is doing. If you haven't used Jupyter before, it's a kind of fancy Python script which lets you evaluate your code step by step and annotate it with visualizations and rich text. This is very useful for this kind of experimental scientific work where you want to inspect your data and make charts. So here I'm using VS Code's Jupyter plugin to run this notebook. So let's run through. The first thing you'll have to do at the top of every tool script is this import statement, where you load the CryoSPARC function from the CryoSPARC Tools module. So we'll run the snippet. Then on the next line, we'll call this function, providing the full HTTP URL of your CryoSPARC instance in a quoted string. This is again the same URL that we use to access CryoSPARC from the browser. We'll put the result into the CS variable. This CS variable is an object that represents my CryoSPARC instance. It has a bunch of other functions inside it that you can access with the dot notation. When we call this one, find project, it returns a project with its own inner functions, which you can use to access its workspaces and jobs. At the bottom of our snippet here, we're just going to print out the title field for the project in workspace, as well as the names of the outputs for this refinement job, which you can also access with the dot notation. So I'll scroll down a bit. This last print statement represents the list of outputs that I have available on my job. You can see if I open up the refinement job, those same outputs are in the sidebar here. Think of these function calls as navigating through your CryoSPARC instance from your web browser. When you first open CryoSPARC, you first have to select the project that you're working on, then you select a workspace within a project, and finally you select the job that you're interested in. And that job has its own functions that you can call on it. You can find documentation for all the functions available in CryoSPARC on the Tools website. For this refinement job, we're most interested in the particles output because this is where CryoSPARC stores the per particle scale information. We'll use the refinement job's load output function to load this particles object. What we get here is a dataset object, which basically represents a table of results from my job. Each row in the table is a particle, and each column is some data that CryoSPARC has computed for each particle. We can see that this dataset has around 300,000 rows, which get truncated here so that you don't have to scroll through all of them. If I scroll over to the side, I can see information for each particle in the columns. You can see the columns all have this prefix/suffix name, and lots of them have the same prefix. Groups of columns with the same prefix like this represent a corresponding output result. So here, for example, the CTF columns all represent information available in the CTF result here. The alignments 3D columns all represent the alignments 3D slot, and so on with the rest of the column groups. The column that we're interested in is the alignments 3D alpha column, which, as you'd expect, contains the scale value for each particle. If I want to access data from this column, we can use this square bracket notation. And you can see that this is just a list of alpha numbers for each particle. I can also use one more level of the same square bracket notation to access a specific row number, where the first row is 0. So now that we have our particle alpha data, let's visualize it. I'm using this library called Seaborn, which I installed earlier. This is a plotting library for Python. You can view the documentation at seaborn.pydata.org. In our code, we'll import Seaborn and set a default theme. Then we'll use the displot function to create a distribution plot of the alpha values, grouping them into 100 buckets. Then we'll also draw a vertical line at alpha value 1. There you can see this is the same distribution plot that we saw in our refinement job earlier. So it looks like there are two distinct groups of particles based on their scale, above and below just around alpha 0.9, maybe a little bit less. So let's adjust that and run. We want to pull out the particles that are to the right of this line. That is, all the particles that have alpha values greater than 0.88. I can do that with the particle dataset's mask function, which requires a comparison like this as an argument. This inner notation here, alignments 3D alpha greater than 0.88, evaluates to a list that's the same size as the alignment's 3D alpha column, but instead of numeric alpha values, each row will have a true or false flag. True if the number at the corresponding row is greater than 0.88, or false otherwise. Then the mask function, given this list of flags, creates a new dataset with only the particles whose row numbers have true in the given list. We can perform a similar operation with the opposite comparison to get the low alpha particles. There are other ways to pull off this kind of row filtering depending on what data you're looking for. You can check out the documentation for datasets on the Tools website if you want to learn more. This leaves us with a smaller dataset of just around 200,000 rows with just the high alpha particles. So we have this dataset of particles we're interested in. We want to write these particles back into CryoSPARC so that we can see how they affect the refinement. We can do that using an external job. So I have my workspace object here that I created earlier. We'll call the workspace's createExternalJob function. We'll add a title for the job, and we'll save the result in the external job variable. And we'll run this code. And right away, a new job shows up in my CryoSPARC workspace, which we can now control from Python. Conceptually, think of this external job as the representation of a single job run of our script. So just thinking about what the script is doing, it's loading the particles from this J7 refinement job, and it's filtering them down to produce a final output that eventually may be used in other jobs. Right now, if I open up this job, you'll see that it's totally blank. There are no inputs and parameters, and no outputs defined. So we'll have to add those in our script. We'll use the external job's addInput function to create a new input named allAlpha, passing in particle for the input type, and we'll pass in a list of input slots. In this case, we only need the alignment's 3D slot because this is the result that has the alpha column that we're interested in. When I run this, we can see the input appears in CryoSPARC here. It's shown as empty because we only registered that the input exists but didn't connect anything to it. So next, we'll call the external job's connect function, passing in the name of the input we just added, and we'll pass in the UID and the name of the output from the refinement job. And when I run this, the external job jumps down and the connection appears in the workspace as if I had dragged the particles output from the refinement job into this external jobs builder. Quick note here, these last two steps here are technically optional. You don't need to have an input connected to save an output that you previously loaded directly, but this is good practice to make sure that your external jobs show up in context like this, and so that any previous results that you didn't use in your script, like the particle's location and CTF data, are passed through correctly. So now we have inputs, but the outputs are still going to be blank. We'll use the external job's addOutput function to create two outputs, high alpha for the particles we filtered earlier, and low alpha for the ones that didn't make the cut, in case we end up needing those in later processing. Like before, these show up in the job's outputs, and you can see all of the other results from the original refinement job are already passed through, and that's because we provided the name of the input that we added earlier to the pass-through argument here for the addOutput function calls. So now we're finally ready to save the results. We'll call the external job start function. This changes the job status to waiting, which means it's ready to accept results. We'll call the external job save output function, passing in the name of the output that we just created, along with the high alpha particles data that we filtered earlier, and similarly for low alpha particles. And here you can see the total number of particles changed for these outputs, so we can confirm that the saved worked. Before we finish up, we'll also log the per particle scale plot that we created earlier. This log plot function accepts plots from Seaborn, Matplotlib, or any image file. And now we have this plot here in our job that we can go back and reference later. So now that I have my output saved, I'll call the job's stop function to let CryoSPARC know that this job is now complete and its results are ready for further processing. So now from the CryoSPARC interface, I can create a reconstruction job I'll connect the filtered particles. I'll run the job. Then I'll connect and run a non-uniform refinement job using the reconstructed volume and particles. Rather than wait for those to finish, I'll switch over to a workspace where the analysis is complete. Here, I use the slightly more advanced filtering strategy. I use the Gaussian mixture model to figure out that there are 3 distinct species of alpha values in this particles dataset, which I wrote into their own output. Then I reconstructed and refined each group. And here you can see that if we just refine the high alpha particles, we still get a fairly good resolution of 3.02 angstroms, but now using less than a third of the particles that we had before. If we refine both the medium and high alpha particles, we get back the same resolution we had before, but now using 2/3 of the particles that we started with. Furthermore, if we were to download this final volume and compare it to the volume from the original refinement job with the full dataset, we would see improvements in the map quality. That means we probably filtered out some additional junk particles in the low alpha group. By the way, you can now do this particle scale filtering without writing a script like this, using the subset particles job, which is available in CryoSPARC 4.7 and newer. But hopefully this has given you a good idea of how you might use CryoSPARC tools to implement something like that job yourself. Before we wrap up, I'll give you an overview of some other use cases that CryoSPARC tools is especially good for to give you some inspiration for how you might use it yourself. You can use tools to load, inspect, and modify almost anything in CryoSPARC. You can process micrographs, particles, and volume densities, as well as geometry data such as 2D and 3D particle alignments and CTF estimates. You can use it to visualize processing results and metadata, just like we saw in our demo. You can write and orchestrate custom workflows, where you have components that filter out micrographs and particles like we saw earlier. You can programmatically build jobs, change their parameters, connect them, and launch them. If you're doing sysadmin work, you can use it to gather statistics about the data in your project, how much space it's taking up, and optionally back it up or remove it. And you can use it to integrate other cryo-EM programs like Rely On. One great example of this is Ryan Karimi's vesicle picker, where he used CryoSPARC tools in combination with machine learning libraries to develop a new kind of specialized particle picker. If you're interested, there's a link to the source code in the video description. So at a high level, that's everything you need to know to start writing your own CryoSPARC tool scripts. To get the full details, the best place to start is the official documentation at tools.cryospark.com, which includes lots more examples and the full API reference. We also have an examples repository with even more types of scripts and applications you can use for inspiration. And if you can't find what you're looking for there, please send us a question on our discussion forum at discuss.cryospark.com under the scripting category. CryoSPARC Tools is open source software licensed under the BSD 3-class license. You can find its source code on GitHub, where you can also report technical issues and propose code changes. Links to all these resources are available in the description. So thank you so much for tuning into this overview, and happy scripting.